Next presenter will be Mr. Sugihara.
Yes, I'm here.
You are here, perfect. And he will give a talk about stack modulation architecture for simultaneous exploration and navigation of a biped robot. So we can, I think, start. We are perfectly in time, so please.
So do you see the presenting screen now?
Yeah, I see the screen, can hear you.
Okay, perfect. So thank you for the introduction. Let me start my talk. I'm Tom Sugihara at Omron Corporation. This is a collaborative work with my first student, Takanobu Yamamoto, who used to be a student in Osaka University. This talk is about the control architecture for autonomous locomotion of a biped robot in an unknown environment. And in such situations, the robot needs to collect information about the environment, build a map, decide where to go, and coordinate the whole body at high frequency in order to avoid falling, collision, deadlock, etc. But the high-level behavior based on the global information usually takes a longer time than the lower-level reflexive behavior based on local information. So here is a challenge of how to integrate different levels of behaviors on an identical robot body. If you simply connect the information processes in a sequential manner, as shown in this figure, the robot obviously loses responsivity. The subsumption architecture proposed by Brooks is a famous alternative where the behaviors are independently synthesized by some layers running in parallel. The upper layer subsumes the lower layer by reusing modules. It looks strange that the output arrow of each layer sticks in another. This is not a standard way of drawing the system diagram, as you know. According to Brooks, this means that the output from the upper layer overrides that from the lower layer. And the low-level behaviors appear only when the upper layer malfunctions. This figure shows what the actual implementation by Brooks looks like. Of course, I respect him. I respect this great idea, but I would say this is too complex and ad hoc. And I also found some other problems in the original concept. The upper layer is still sequential. Namely, it's less responsive. And so, even while the upper layer runs correctly, crises may happen on the robot. The outputs from the layers basically conflict with each other, and which output should be chosen in such an emergency is not clear. So my opinion is that to override lower layer is not a good idea. The stack modulation architecture, which we propose here, is illustrated by this schematic diagram. Different from the subsumption architecture, each layer does not synthesize any behavior alone, but modulates the lower layer online. It doesn't have any internal conflict in principle, since the motor commands is issued only from the bottom layer, and the propagation of modulations coordinates the robot behavior. Sorry. Based on the proposed architecture, for example, the implementation by Brooks can be quasi-equivalently modified like this. I would say this is quasi-equivalent because some redundant modules are omitted by myself. This is obviously much simpler than the original. Any output doesn't override another, and the system has a sole output, so conflicts never happen. But please note that it's not easy to implement this architecture into a real system. We put an emphasis on the system responsivity and the timeliness of information should be the most prioritized over correctness and completeness. It means that the modules have to accept incorrect and incomplete pieces of information during the process and never bankrupt. So we currently need to develop system components by ourselves because the existing software modules rarely meet this requirement. Let me show a challenging example application of the proposed architecture to the simultaneous exploration and the navigation of a biped robot. The details of components were already published in some papers. Each module has input, modify, and output, where the modify is a quantity that can be modulated anytime. In the lowest layer, the whole body coordination by the inverse kinematics is running, whose modify is the desired CMP and the feet movements. And output is commands to all joint motors. In the second layer, the foot-guided controller, which we proposed some years ago, is running. It accepts dynamic changes of the desired foot placement and the time to land. It simultaneously decides the instantaneous desired location of the ZMP, and in addition to the feet movements. The foot placement, in addition to the time to land, is determined in the third layer, based on the foot reachability, traversability of the terrain, and the capturability. It allows the nominal path to the destination to be changed anytime. The nominal path is planned in the fourth layer based on a coarse terrain map with the A-star algorithm, where a lazy collision detection is applied with the bounding value. This layer also accepts the desired destination from a human operator. The format of the map was developed by ourselves. It is basically a grid map with stochastic elevation and the normal vectors, and can be modified dynamically during the operation by the top layer module. This animation shows the process where the map is dynamically updated. Lastly, this is not a stack modulator, but the fast state estimation is also running on the feedback path. These are a demonstration of the system in dynamic simulations. One thing I have to say that we naively assume that global localization is perfect. Of course, this is a naive idea and should be replaced with the actual localization in the future. Well, the left movie shows a demo in which the robot follows a moving goal presented by a red flow. As you see, the scene is partially observed during the operation. The robot, you sometimes see a green arrow, which is applied by a kind of invisible man during the operation. But the robot stabilizes itself against this perturbation and this robustly follows the moving goal. And the right movie is a demo of a long distance simultaneous exploration and navigation. The robot simply assumes there is nothing in the unobserved area. As the robot moves and the view area grows, the map also grows and the navigation is improved like this. So once it finds complex terrain in front of it, it can adapt behavior according to the dynamic scenes and robustly reaches the final destination like this. Well, it might be too short, but let me conclude this talk. The stack modulation architecture was proposed for an autonomous mobile robot to integrate different levels of behaviors through a review of the subsumption architecture. A point is that the upper layers do not override the lower layers. as the subsumption architecture, but modulate them to avoid conflicts between modules in principle. It requires each module to be designed such that it accepts incomplete and noisy information from the upper modules asynchronously, which is not easy. An example system of simultaneous exploration and navigation by a biped robot was presented. A short-term future work is, of course, the global localization. That's all. Thank you for your attention.
Can you hear me again? Okay,
Yes, I hear you.
Perfect. Now, I think my mic was switched off. So thank you for the presentation. And we have, of course, time for some questions or remarks. Who likes to start? Maybe I start with one question. You mentioned this behavior-based concept, subsumption architecture of Brooks. The powerfulness of such a behavior-based concept is that you have an easy integration of activities which you have to manage in a reactive way, which means if you have some disturbances, you can directly react on disturbances. For example, if you have a push or if you slip away or whatever happened during the locomotion process, you can implement a behavior which will be active and takes over directly the control. And that's why you have an override. This is the idea of the subsumption architecture. How do you manage such things in your concept?
Well, it's related with the design of each component. For instance, in our system, the key module is this part, how to determine the foot placement. So a high-level behavior that uses global information should be managed based on the complex map. But at the same time, the robot has to respond to instantaneous perturbations at any time. And how to combine such global information with local information is not so easy to answer. And well, this is a detailed part of this part. So if you are interested in this part, I can explain in more detail. Sorry, I know I don't answer your question so nicely.
Yeah, because I wonder from your architecture where the reactive components are and how they can integrate it, or new ones can be integrated in your system. This is not clear how this works, because what you show is more or less a nice sequential concept, a hierarchical sequential concept, where different things are activated based on states what in the upper level is selected. So these reactive components is a little bit missing, why I do not see it in your structure.
Well, I might misunderstand your question, but all components are reactive. That's the point. So this is not a sequential. This system doesn't run in a sequential manner because each layer runs in parallel. So even if the foot placement is not explicitly designated, the lower layer still runs.
Yeah, but it's a very simple question. So if you have planned your foot trajectory and you get now a push, and of course you cannot follow this foot trajectory, what happened now? Where is the foot?
So in this system, the foot trajectory is instantaneously modified. So
Okay.
actually, we don't use any trajectory planning in advance, but the motion is always coordinated in real time.
And how is the foot trajectory adapted if you have a push, for example? What happened?
Again, we don't have any pre-planned foot trajectory. It's synthesized in real time. So, for instance, when the robot is strongly perturbed, the desired foot placement is determined based on the capturability concept. And the controller just tries to reach that landing foot placement in real time without any pre-planned trajectory. Sorry, I'm answering your question.
Yeah, half. So I think we have to go into detail to really understand what happened in this foot planning process, how the states, the changing states of the biped will be considered. But maybe other guys have also a question. Is someone else having a question or remark? Maybe I'll check the chat again. No,
Here we go.
don't
Here we
really.
go. Question maybe.
Yeah, sure.
I think I have a trouble with hearing you.
With microphone. Do you hear me?
Now it's good.
Thank you. Thank you for an interesting presentation. And I have one question. What's the difference between SLAM and CIAN, simultaneous localization and mapping, and simultaneous exploration and navigation?
Oh, okay. SLAM is the technique to build a map and localize itself simultaneously, right? But the simultaneous exploration and navigation is about the motion, about the synthesis of the robot behavior. So based on the map and the localization information, it will produce how to which direction it should go based on the partial observation.
Robot behavior. Okay.
So okay,
Okay,
navigation is basically exploration and navigation are both about the behavior, right?
Yeah.
And the SLAM is of course used as a part of the that framework.
Thank you.
Well, thank you very much.